Hello all, I'm back with another video, and for the first time this is a mathematics paper. Okay, I keep saying that I can probably uh, deliver to you guys mathematics papers, mathematics lessons, lectures, whatever, but I think this is the first time I'm doing it, with the exception of one problem that I solved when I was testing what to do with the channel and so on. But anyway, this is a special type of paper for me because one of you guys wrote in one of the comments, why don't I go over a mechanics paper? Okay, so I went online and I checked and found this mechanics M3 paper. It's the most recent one from the January 2026 season, and it's from the Edexcel International A-level curriculum. Okay, so my speculation, estimation, whatever, is that these types of papers are taken by people who are interested in studying engineering or mathematics, stuff like that. But it really is just physics and math. So anyway, I went over it. I didn't really follow the mark scheme. I did my own thing. Uh, you should let me know in the comments if my solutions make sense, if this is useful, and whether I should make more of this. But anyway, let's dive in. So, question one, and by the way, from what I saw, this paper takes an hour and 30 minutes, so you only have an hour and 30 minutes to solve. And in this paper, I found 8 problems. I don't know if that's standard or not. Maybe in other papers they have 9 problems. I don't know. So, but let me know. Let me know. So let's start. A particle P is moving along the x-axis. At time t seconds, the displacement of P from the origin O in x meters, where is x meters. I'm sorry, where x is 0.6, and then the cosine of kt plus pi over 4, and k is a positive constant. Question A, prove that P is moving with simple harmonic motion by showing that the second derivative of x is equal to minus k squared times x. To do that, we simply have to find the first derivative. This dot means dx over dt. I was surprised to see this at the high school level because I learned this dot method, this dot thing, when I went to college, in my case. So the first derivative is minus k times 0.6, and then the derivative of a cosine is minus sign, right? That's why we have the minus sign up there, and then the sign of the argument. Okay, now the second derivative is minus k squared, right, times 0.6 times cosine of kt plus pi over 4, which is nothing but minus k squared. I mean, you can recognize this as x, right? So minus k squared x. So we proved it. So that's the first win in this paper. And I have to admit, it was a lot of fun because I found it challenging. I had to go many years into the past to, recall methods and formulas and stuff like that. So it was fun. So thank you to the subscriber who suggested I should go over this. So this was part A. Part B, state the amplitude of the motion of P. The amplitude is simply 0.6 meters. Okay, so that's A, that's B. So we read it off the function pretty much. Okay, I don't know if they require something more than that, but I think it's simple enough. So question C, find in terms of k the maximum speed of P. Okay, so this is since this is simple harmonic motion, V max is equal to k times the amplitude. Okay, so that's just 0.6 times k meters per second. D, the period of the motion is 4 seconds, and now D. Okay, so they give you an additional piece of information, and they ask you to find k in terms of pi in question D. So let's go do that. D, so omega is equal to k, right? And we know that because For simple harmonic motion, we have cos omega t plus phi. So we identify k as omega, right? But omega is 2 pi over t, which is equal to k. And t is just 4 seconds, so k is pi over 2 seconds to the minus 1 is the unit. All right, and E, this was a little bit trickier. Find the time taken by P to move directly from A to B, and they give you an additional piece of information. The points A and B lie on the x-axis on opposite sides of O, with OA equals OB equals 0.2 meters. So the situation is this: you have the origin, point A and point B. So this is negative 0.2 meters, and this is positive 0.2 meters, right? So we go to the displacement that they give us, the initial function, okay? And we substitute plus or minus 0.2 equals 0.6 cosine of pi times t over 2, since we now know what k is, plus pi over 4, okay? So the cosine of pi times t over 2 plus pi over 4 is simply plus or minus 1/3. You can see this if you divide 0.2 by 0.6, you just get 0.33333, which is 1/3, right? So this is a trigonometric equation with solution. You can use your calculator to find it. So pi t over 2 plus pi over 4 is 1.23 is the first solution, and the second solution is 1.91. When I say first, I mean for the plus and then for the minus, okay? But we're not done yet, because we have to keep going. So pi times t over 2 is 0.45 and 1.13. Those are the two solutions. Maybe it's better to write it like this, so I don't confuse you. So 0.45, 1.13. So t, if you multiply by 2 over pi, you get 0.29 and 0.72. So delta t, so this will be your first time, okay? So this will be t1, and the second time will be t2. So at time t1 it will be here, for example, and at time t2 it will be on B. So therefore delta t is simply the subtraction between these two, t2 minus t1, which yields 0.43 seconds, which is our answer. Okay, this was a good start for me. I mean, because it has been so long since I worked on something like this. And then came this, and I thought it was hard, and to be honest, a little bit hard, okay? So a particle P of mass m is attached to one end of a light inextensible string of length 5a. The other end of the string is attached to a fixed point A above a smooth horizontal table. The particle moves in a horizontal circle on the table with the string taut. The center O of the circle is vertically below A, with OA equals to 4A. As shown in figure 1, the particle moves with constant angular speed omega and remains in contact with the table. A. Find in terms of m and g the magnitude of the normal reaction between P and the table when omega is 1/4 times the square root of g over A. So my first step, say, was to redraw this to understand what's going on. So I did this, okay? So something like this. So this is the origin, okay? So this is A, and you have your string there, so that's your P. And what's going on is the following. So you have this guy going around in a circle in this direction. Okay, that was my understanding of the problem. And this is the scheme I used to draw forces. Okay, so how many forces do we have here? We have tension from the string. Okay, I'm gonna use red to draw the forces. Okay, we have the reaction force from the floor. We have the mass of the particle. Okay, and now the motion is on the plane. Okay, so omega is on the plane like that. Therefore, we need a centripetal force in this direction. Okay, so actually let me use yet another color. So our centripetal force should be inwards. Therefore, this guy is gonna keep going in circular motion. So you need a force like that. Okay, and again, for circular motion, the force, the centripetal force, is tangent to the velocity. Okay, so anyway, and we immediately see that we need to analyze, let me see, we have to analyze the tension into a component that points inwards. So if we name this angle theta, so that angle is theta, this component is t cosine theta, and then the other component, we have another one, which is t sine theta. Okay, and cosine theta can be calculated from the scheme. We will see how to do that in a moment, but let's write down the equations of motion. So in the perpendicular direction, we have r plus tension times sine theta is equal to mg, because the particle is not moving up or down. Okay, so you have balance on that direction. So r plus t sine theta is equal to m times g. And then in the horizontal direction, where the motion is going on, we have t cosine theta, the tension times cosine theta, plays the role of the centripetal force. Okay, so it's equal to m omega squared times r. So we can write, okay, let's keep them like that. So this is 1 and this is 2. Let's rewrite 1. Okay, is this the best way to do it? No, that's not the best way to do it. We will start with 1 actually. I'm sorry. So r plus t sine theta is mg. And then from 2, we can solve equation 2 for t. So t is m omega squared r over cosine of theta. Okay, and we can plug in for t. Okay, so r plus m omega squared r sine theta over cosine theta is m times g, and then this is just tangent of theta, right? Okay, so let's write that down. R plus m omega squared r times the tangent of theta is m times g. And now we can use some information they give us. So r from the scheme is, what is it, 3a, because if that's r, we have r squared plus 4a squared is equal to 5a squared. Actually, this should be like that. Okay, so we can see immediately that r squared is 9a squared, therefore r is 3a. Okay, and then we can also see that this is theta, right? So the tangent of theta is 4a over 3a. Okay, so that's just 4/3. Okay, I hope this makes sense. So let's go plug in. Let me erase that, you don't need it. So r plus m, and then omega squared is 1/4, which becomes 1/16, and then the square root cancels due to the square, because we square the square root. Okay, times r, which is 3a, times the tangent of theta, which is 4/3, is equal to m times g. So a cancels, and what else cancels? Let me see. 3 cancels, and then we can cancel that and make it a 4. Okay, so R is mg minus mg over 4, which is what's left from this massacre over there. So mg fourths. So R is 3 mg fourths. Okay, this was quite something. So, but that's the answer. Okay, now let's go to question B. Let me transfer this whole thing down so you see. Okay, let's put it there. Okay, fine. Now B, for B, they give you an additional piece of information there. Oops. They tell you that the angular speed omega is gradually increased and the particle remains in contact with the table. Show that omega is less than 1/2 square root of g over a. So what they actually mean is that if omega exits, goes beyond 1/2 times the square root of g over a, then the particle will lift itself like that. Okay, so it will go up. It will not touch the table anymore. Okay, so that's the key for the solution, actually. So let's let me write down. Okay, we have enough space. So B, the moment the particle loses contact with the floor, R becomes 0 because R is a contact force, and without contact you have no contact force, right? So R becomes 0, and T barely holds the ball, on the floor. Okay, so we will use our equations 1 and 2, but we will set R equal to 0. This is what I'm trying to say. So from 1 with R equals to 0 becomes T sine theta is equal to mg. And then 2 remains the same because we still need to have circular motion. And we can have circular motion even if the particle takes off the table, guys, right? So imagine one of those, if you go to amusement parks, they have those chairs that you sit and you sit on the chairs and then they start spinning with speed, and then they grow outwards. I don't know how else to describe it. So something like that. I am tempted to go to Google and show you, but yeah, or no, let's continue. So, and equation 2 is the same as before. T cosine theta is m omega squared times r, okay, and r is 3a. But anyway, I put them like that because we can divide them, okay? If we divide these two equations, t cancels and mass cancels, and we find this beautiful formula. Tangent of theta is g over omega squared r, and omega is now unknown, okay? So tangent of theta is the same as before, so 4/3 is equal to g over omega squared times r, which is 3a, right? So omega squared becomes equal to 1 over 4a times g. So omega becomes equal to 1/2 and then the square root of g over a. And actually, we have to say that omega must be less than 1/2 square root of g over a to remain in contact. Okay, and this was question 2. Okay, I mean, I was I was caught off guard. I mean, when I went to solve this paper, it gave me a challenge. I did solve the problems. I solved them all, but it took me some time to, refresh my mind, etc. But it was a fun change because I don't know. I took off lately. I keep solving papers over and over and over again. So, and I enjoy it, but sometimes you need something different. And I keep promising, but at some point I'm gonna put out some material related to making games with code. I know most of your students who who are following this, high school students who are following this channel, but I don't know, maybe you will find it interesting. We will see. All right. Question 3. In this question, you must show all stages of your working. Solutions relying entirely on calculator technology are not acceptable. I suspect that they mean that you have to perform the integrations. Show your work, because if you do it on a calculator, they punish you, I guess. So, or they don't give you the full marks. So let's go. A particle P is moving along a straight line at time t seconds, larger than or equal to 0. P is a distance x meters from a fixed point O on the line and is moving away from O with speed 8x over 3 plus x squared meters per second. A, find the magnitude of the acceleration of P when x is 3. Okay, so we need the acceleration, but we are given v in terms of x. Okay, so this is complicated because the acceleration is just dv over dt. Okay, so what? How are we going to handle this? Okay, we can do dv over dx, right, times dx over dt. In physics, we wait. What did I mess up here? Sorry. Times dx over dt. Okay, so in physics we say that we can do that because so we can cancel those differentials and uncover dv over dt. I think mathematicians don't like that, but I'm a physicist, so let's go with that. So dx over dt now is v, right? So we have v times dv over dx. And now we can do business because we're given v of x, which is 8x over 3 plus x squared. Let's use square parentheses, to avoid confusion. And let's do dv over dx. So it's this is a fraction. So you take the derivative of the numerator, which is 8, times the denominator, minus the derivative of the denominator, which is 2x, times the numerator over the denominator squared. Okay, I haven't done a derivative by hand in ages. So again, thank you guys for introducing me to this paper. So if you carry on the calculations, you will find that this is equal to 8x over 3 plus x squared to the cube, and then times 24 minus 8x squared. Okay, so all we have to do now is to find what the acceleration is at x equals to 3. So we plug 3 in and we find 24 over 12 to the third times 24 minus 8 times 9, and this yields minus 0.67 meters per second squared. Now, part B. Given that x is 1 when t is equal to 2, find the exact value of t when x is 3. Okay, this was also kind of a little bit complicated. So we can start with dx over dt. Actually, we can start from v is equal to 8x over 3 plus x squared. So dx over dt is 8x over 3 plus x squared. Okay, so let's take dt to the right hand. Okay, we will cross multiply. So we have dt. Let me see how I want to do this. You guys are high school students, but don't know, I don't want to overestimate your abilities, so I'm gonna do it completely. So 3 plus x squared times dx over 8x is equal to dt. Okay, so I'm gonna bring dt to the left hand side. So dt is 3 over 8 dx over x plus 1/8 x dx, and now we can integrate. Okay, so the integral of dt is just t, and then we have 3/8 ln of x plus x squared over 2 times 8 becomes 16 plus a constant. And this is why they give us this information, okay? That allows us to eliminate the constant. So x is 1 at t equal to, what is it, 2, okay? So if we plug in, we find that 2 is equal to 3 over 8 times ln of 1, which is 0, plus 1 over 16 plus c. So c is 31 over 16. Okay, so the function for t becomes 3 over 8 ln of x plus x squared over 16 plus 31 over 16, okay? If x is 3, then t becomes 3 over 8 ln of 3 plus 5 over 2 seconds. And that's the answer, okay? It involved a little bit of tricky math, but I hope it was clear. Again, let me know what you think about this particular video, my videos so far, the way I teach, other content or material you want to see in this channel. And by the way, I'm a nuclear physicist with a PhD, so I can literally almost teach or talk about any topic in physics imaginable, I guess, except general relativity. I don't want to claim that I'm a guru or anything. I just explain to you what I can teach. A-level material, okay, of course. Then I'm thinking about coding. I already have some videos about coding. They tanked. Nobody watches them. I don't know why. Maybe they are not good. So you let me know in the comments what you think about these videos, other videos, etc. So let's move on. Question 4. This was something. So okay. So you see that object over there. So a uniform solid right circular cylinder has radius 3a and height 9a. A uniform solid hemisphere of radius 3a is attached to the cylinder. Okay, so this is uniform, okay, meaning that it's not hollow. Okay, so a uniform solid hemisphere of radius 3a is attached to the cylinder so that the plane face of the hemisphere coincides with one of the plane faces of the cylinder. A solid right circular cone of radius 3a and height 6a, whose plane face is the other plane face of the cylinder, is now removed from the cylinder to form the uniform solid S. The point O is the center of the circular base of S, as shown in figure 2. Question A, show that the distance from O to the center of mass of S is 77 over 12a. Okay, so that was the first question. And let's write a few things down. So first of all, the center of mass of this object is going to be along this axis of symmetry. Okay, so if I draw a line, so I want to bring it, it doesn't obey. Okay, let's try again. So this line, perfect. Okay, so this is the line of symmetry. Okay, this is a symmetrical object. So the center of mass is going to be along this line. Okay, that's the first observation. Now the second observation is that this is a composite object that consists of a hemisphere. And okay, to solve this, I assumed that the center of mass of a hemisphere, the center of mass of a uniform hemisphere, the center of mass of a uniform right cylinder, and the center of mass of a uniform cone are known. Okay, because if you have to prove this in a 1 hour and 30 minutes test, you will spend all your time working on this. So I assume this is something that is given. This is by the way, I didn't mention it yet. do they give you some formula sheet or something like that that includes some information? I don't know. I just I just what is the past? Dived. I think it's dove. I dove into the problem set, and I just started working. So I don't know what kind of information they give you, but I assumed that the center of mass of these three objects is known. Okay, so let's start with the hemisphere. The hemisphere, okay, which is again uniform, okay, which is important. It's not a shell, okay. So the volume of this object is 1/2 times 4/3 pi r squared, because it's half the volume of a sphere. So 1/2 times 4/3 times pi times 3a cubed. By the way, that's cubed. I don't know why I wrote 2. Okay, mistakes happen. So this is equal to 18 pi a cubed. So the mass is the density, which we assume is the same for the whole object, rho times v. So 18 pi rho a cubed. It's not really needed because it's going to cancel out, but okay, let's put the density in. And then the center of mass, center of mass, is 9a, because it's on top of the cylinder, right? So 9a plus 3/8 times the radius of this hemisphere, which is 3a. Okay, and this is 3/8 times the radius is the center of mass of a hemisphere. Okay, so if we add this up, we find 81a over 8. Okay, now the cylinder. The volume of a cylinder is pi r squared times height. So pi times 3a squared times 9a yields 81 pi a cubed. And again, the mass is rho times the volume. So 81 pi rho a cubed. Okay. And then for the cone, the volume is pi r squared times h over 3. So that's pi times 3a squared times the height is 6a over 3, and this yields 18 pi a cubed, which incidentally is the same as the volume of the hemisphere. Okay, I guess, oops, we don't need this. Let me delete it. Trash. Okay, and let's use the pages they give us. Okay, that's enough. All right, now the mass of this object is rho times v, so it's 18 pi rho a cubed, and the center of mass for the cone is 1/4 times 6a, or 3a over 2. All right, so this one, though, we're going to take the mass to be negative, right? Because we subtract it. It's not there, right? We subtract that piece from the composite object S. So the center of mass for S is then, let's make a nice, we will need a lot of space. So it's going to be the mass of the hemisphere, which is 18 pi rho a cubed, times the center of mass of the hemisphere, which is 81 a over 8, plus the mass of the cylinder, which is 81 pi rho a cubed times 9a over 2, minus, let's extend the fraction in and below, so minus 18 pi rho a cubed times 3a over 2, and then the denominator, I'm going to write it in red, and we have to write 18 pi rho a cubed plus 81 pi rho a cubed minus 18 pi rho a cubed. So it's the total mass. So this cancels. So we get a really nice cancellation over there. Then we can also cancel those factors of rho a cubed. Can we cancel the pi as well? We can, right? So this and this can be cancelled with this, okay, because it's a common factor. And now we can do business, as I say. So this whole thing becomes, let me see, okay, 729a over 4 plus 729a over 2 minus 27a over 81. And if we keep going, we find that actually, let's use this space. So it becomes 2079a over 4 over 81. So this is 77 over 12a. Okay, B. Okay, let's go read it first. So starts here. The solid S is placed with its circular base on a rough horizontal surface. The point Q, shown in figure 2, lies on the circumference of the top of the cylinder. Okay. A horizontal force of magnitude H is applied to S at Q. Okay, let me erase this, and we will use this to demonstrate what's going on. Okay. Okay. The force acts towards the axis of symmetry of S. Maybe we should have kept the axis. So that's the axis, and this is the force they mention. This is H. Okay. Okay. The horizontal surface is sufficiently rough to prevent S from sliding. The solid S is on the point of tipping. Given that the weight of S is W, find H in terms of W. So the weight, let's use orange, is gonna act from the center of mass. By the way, the center of mass is 77 over 12, which means 77 over 12 is 6.41. So it's right above the tip of that cone that is missing. Okay, so that's where the center of mass is. So the mass acts from there, right? So that's the weight. Okay, so that's the weight, and we can take moments about this point, the tipping point, right? So H is 9a away from the tipping point, and then the weight is simply 3a from the tipping point. So let's call it T, the tipping point. Okay. So this is actually much simpler than it sounds, because if you take moments, you have H times 9a must be equal to the weight times 3a for balance, right? So a cancels, and then 3 simplifies, and we find H as 1/3 the weight. Okay. So if you apply more force than that, it's gonna tip. Do they mention how much it's gonna be? No. Okay. Again, I didn't really follow the mark scheme. Let me know if all these things are correct. So let's move on to question 5. This gave me a lot of trouble because I had trouble understanding what was going on, to be honest. So, but once I understood, it was simple. So you have a uniform rod AB with mass M and length 3L. The rod is free to move in a vertical plane about a fixed, smooth horizontal axis through B. One end of a light elastic string of natural length 2L and modulus of elasticity 5 mg over 8 is attached to the rod at A. The other end of the string is attached to the fixed point C, which is at a distance 3L vertically above B, as shown in figure 3. The rod is resting in equilibrium with angle ABC equals to 2 theta, where theta is larger than 0 and less than pi over 2. By taking moments about the horizontal axis through B, show that the extension of the string is 16 over 7 times L. This is quite of a difficult problem, I think. So what's going on will never make sense until I do this. So let's draw a line, okay? So let's say that, let's pretend that this is AB. So AB can rotate like this, okay? So it's a pivot point. B is a pivot point, okay? So you have to imagine it in 3D to make sense, which is what I did. Otherwise, it would never make sense to me. Okay, I hope this demo makes it easy. If not, another thing you can do that I just thought, so I have to improvise, is if you do a 3D representation of this. So this will be C, and this will be B. So this is the rod AB. Okay, so you see that this angle is not really, so that angle is 2 theta, and it's not really perpendicular, okay, which creates a lot of confusion, okay. And this is AC, the string, okay. I hope this helps. Visualizing it helped me tremendously to understand what was going on. So that's the first observation. The second observation is, the observation about how things work in this problem. The second thing to realize is that this side is 3L and this side is 3L. Now AC is 2L plus whatever the extension is, okay? But the important thing is that this is an isosceles. Is that how you pronounce it? I think so. It's an isosceles triangle, which means that these angles, let's call them phi, are equal to each other, okay? And in fact, 2 phi plus 2 theta is equal to pi because it's a triangle. So phi plus theta is pi over 2. So phi is pi over 2 minus theta. Okay, we will need this in a moment. All right. Okay, so the first force is the tension from the string, which we can draw like this. Okay, that's the tension. And this is phi. So we need to find the component of T that is perpendicular to the rod so we can take moments around B. Okay, that component is this one, which is T sine of phi. Okay, the other component is this one, it's T cosine phi, but it's along, it points towards B, so it doesn't create a moment, so we're going to erase it for now. Okay, the other force is the weight. The weight acts vertically downwards. Okay, so something, it's like that. Okay, the weight is not perpendicular to AB. Okay, and the way to see this is to come here on the 3D case. So that's the weight. Okay, you see that it's not perpendicular and that you actually have this component. That component is perpendicular. Okay, and the other really crazy observation to make, if we come to this 3D version, is that this angle, let me raise this 3L over there, okay? So if this angle is 2 theta, so is this angle, okay? And the way to see it, what's the way to see it, is that if we draw, okay, if we make this dashed line up and this dashed line up, then you see that these two lines that I'm denoting with asterisks are parallel to each other, and they are cut by this line. Okay, so you can use Thales' principle pretty much. Okay, it's kind of crazy, but this angle and this angle are equal to each other. Okay, therefore the component of the weight that exerts a moment is W, so it's that one, W, and then let me erase that. So W sine of 2 theta. Okay, so I hope all these things make sense because this was a crazy problem. Okay, So, so in other words, I'm gonna exaggerate how W looks here. So W is, let's say, this one, and therefore you have W sine 2 theta, okay? And this angle is 2 theta. All right, so to take moments, we take t sine phi, so t sine phi, now I confuse myself, times 3L, right, is equal to W sine theta, sine 2 theta, excuse me, times 3L over 2, since the center of mass is in the middle of the bar, right? So we can cancel this 3L. And then we can also immediately see that sine of phi is equal to sine of pi over 2 minus theta, which is equal to cosine of theta, okay, which was a nice surprise to find, to be honest. Okay, so from 1 and 2, if we combine them, we will find that W times sine of 2 theta over 2 is equal to t cosine theta, right? So we can write that t is W, and then we can expand sine 2 theta as 2 sine theta cosine theta, and then we have 2 and then cosine theta, so we get this nice cancellation. So T, the tension, is mg sine theta. Not the tension, I'm sorry, I keep saying the tension, I mean the elastic force from the Hooke's force, right? Okay, now the force is equal to lambda x over L, and lambda is given is the elasticity coefficient, right? Modulus of elasticity, I'm sorry. So 5 mg over 8 is the modulus of elasticity. X is what we need to find, and L is the length of the string, which is 2L. Okay, so let's plug this in. So we have 5 mg over 8 times x over 2L is equal to mg sine of theta. Mg cancels, and we find that x is 16L. 8 times 2 is 16L, and it comes to the numerator times sine of theta over 5. And let's call this equation 3. Okay, we are not done yet. This is a crazy problem. So, how are we going to find sine theta? Okay, this is the part where you will need to tell me what you're being taught at this level, because I use the law of sines. Okay, so law of sines. Okay, so we have a triangle pretty much. Actually, let me do this. Okay, so okay, drew a triangle. So we have this triangle. It doesn't look like the original, so I don't like it. So let's delete it. So something like this is the triangle we need. Okay, they tell us that this is this side is 2L plus whatever the extension is. This side is 3L and this side is 3L. And then we have that this angle is phi, this angle is phi, and this angle is 2 theta. Okay, so the law of sines says that the sine of this angle, so sine of 2 theta, over the opposite side, over the opposite side, I mean the angle is kind of looking towards that side, so sine of 2 theta over 2L plus x is equal to sine of phi, so sine of phi over the angle, sorry, over the side it looks towards 3L. But then we can again use sine of 2 theta is 2 sine theta cosine theta over 2L plus x. I'm using parentheses to avoid confusion. Sine phi is cosine theta over 3L. So cosine theta cancels again beautifully. So sine theta ends up being 2L plus x over 6L. Okay, and this equation 4. The sanity check here is that L and x have dimensions of meters, so they cancel each other, and sine theta is a pure number. Okay, it's good to do some dimensional analysis sometimes. Okay, so if we use 1 and 4, we have x is 16L over 5, and then times 2L plus x over 6L. Okay, so we have 30 xl becoming equal to 32L squared plus 16xl. So L cancels, and we find 14x is equal to 32L. So x is 16L over 7. That's the answer. Okay, it was a long problem, but we found what we were looking to find. Okay, let's move on. I hope this made sense. The key for me, at least, was to draw things in 3D and realize that the weight is not really perpendicular to the rod AB, but rather it has an angle 2 theta. It makes an angle 2 theta with the rod AB. Okay, so it took me a while, I have to admit. Like, it took me some time to figure it out. Okay, question 6. So we have this uniform lamina. Okay, so they say in this question you must show all stages of your working solutions relying entirely on calculator technology are not acceptable. Okay, let me check something. So a uniform lamina ABCD is in the shape of the region R. The region R is bounded by the curve with equation y equals 1/4 times x squared plus 8. The line with equation x equals to 4. So this line and then this line, right? So the x-axis and the line with equation x equals -2 as shown shaded in figure 4. The area of R is 18. Okay, we can use that. A, show that the x-coordinate of the center of mass of the lamina is 3/2. Show that the y-coordinate of the center of mass of the lamina is 17/10. Okay, let's do this part first. Actually, let's do A first. Don't know why I rushed into A and B at the same time. So, okay, actually, let's start here. A. Okay, the x-coordinate of the center of mass is equal to -2/4 xy dx over -2/4 y dx, which is the area, right? And they give us that. So we only have to find -2/4 xy dx over 18. All right, so let's go calculate this beast. Okay, so we have this, the integral from -2 to 4 of x y dx is equal to 1/4. Then the integral from -2 to 4 of x squared plus 8x dx. Okay, and this is equal to, wait, what did I miss? I messed up something. We have to multiply by, this is x cubed, okay? Because x times y is x cubed plus 8x. Okay, so that's 1/4, and then x to the 4th over 4 from -2 to 4 plus 8/4 x squared over 2 from -2 to 4, and this is equal to 1/4 times 1/4 times 4 to the 4 minus of -2 to the 4th plus 2 over 2 times 16 minus 4, which is 15, plus 12, which is 27. Please check my answers. So now x is equal to let me see, 27 over 18, right? So this is 3 times 9 over 2 times 9, so 3 halves, which is exactly what we wanted to find, so we are happy with that. And we move on to part B. So the y coordinate of the center of mass is simply the integral from minus 2 to 4 of 1/2 y squared dx, and then over 18, since they give us that information, we can use it. So let's calculate 1/2, and then the integral from minus 2 to 4 of y squared dx becomes 1 over 32, and then the integral from minus 2 to 4 of x to the 4 plus 16x squared plus 64 dx. Okay, so this is going to be 1 over 32, and then x to the 5th over 5 from minus 2 to 4 plus 16 over 3x cubed from minus 2 to 4 plus 64x. I'm sorry it's tedious, but what can we do? I mean, we have to carry out the calculations. Okay, so that's 1 over 32, and then we have 1056 over 5 plus 16 thirds times 72 plus 64 times 6. Okay, and this yields 153 over 5. So the y coordinate of the center of mass, 153 over 5 times 18, which we already have, yields 17 tenths. Okay, which is what we wanted to find. Okay, that was part B. Part C. Wait, I need to erase this so you guys actually, let's do something else. Let's transfer this further down. Actually, let's do the whole thing. Okay, let's transfer it there. Okay. Okay, part C. The lamina is freely suspended from B, so there, okay, and hangs in equilibrium with BC. Okay, with BC at an angle theta to the downward vertical through B. Find the exact value of tangent of theta. So this was a weird question for me. I've never seen this before, to be honest, in my life. But I figured that, okay, the center of mass is going to be somewhere here, okay? Since x and y are both positive and within the lamina, right? 3 over 2 is 1.5, so so where they have the r pretty much is somewhere there is the center of mass. Maybe there is the center of mass, okay? So center of mass, okay. And what they tell us is that you have to find, if you connect this line, okay, then there is an angle theta, okay? So we have to find that theta, and you can see from the geometry that tangent of theta is equal to 4, because from O to C, that's the distance is 4, minus the x coordinate of the center of mass, which is 3 over 2 over 6, which is the vertical distance from B to C, minus the y component of the center of mass, which is 17 over 10. This yields 25 over 43. Okay, and that's, they ask for the tangent. If you, let me use my calculator. They don't ask for it, but the angle is, I mean, you can do it to see if it makes sense. So the angle is 30.2 degrees. So it makes sense. Or in radians, yeah, you can figure it out. So let's move on. This was an interesting problem as well. 7. Okay. At this one, I will need your help with the explanation I'm giving because I don't know what they teach you in school. I hope my explanation makes sense. So one end of a light elastic spring is attached to a fixed point A. A particle of mass m is attached to the other end of the spring. The spring has natural length 3a and modulus of elasticity 18/5 times mg. The particle is held at rest at the point B, where B is a distance 5a vertically below A. The particle is released from rest. Air resistance is assumed to be negligible. Use the principle of conservation of mechanical energy to A. So we have to use it twice, I guess. In question A, find in terms of A and G the speed of the particle at the instant when it is a distance 3a vertically below A. So the way to work this out is, okay, let's draw a scheme. So this is the point A, this is the spring, I guess, this is the mass attached, and they tell you, okay, 3a is going to be, since the length of the spring is 3a, that's 3a, and it's gonna hang a little bit further down due to, I mean, you have a mass there, so it's not gonna be at its natural length, okay? And then the idea is that you pull it all the way to 5a, okay? So I'm drawing lines now. So that's 3a, and now this is 5a. So you bring it all the way down here, and then you release it. And they ask you to find the velocity when it reaches this point, okay? So we take the gravitational potential energy to be 0 up there, okay? So to make things simple. So let's start writing down things. At 5a, the total energy, I mean, when the spring is extended all the way here at the position 5a, okay, the total energy is going to be lambda x squared over 2L plus mg h, right? Now, lambda is the modulus of elasticity, which is 18/5 mg, and then x squared is 2a, so 4a squared, and then over 2a, that's 6a. And then we have to make the gravitational potential energy negative because it's 0 here, it's positive here, so it's negative here. So minus mg times 5a. So this is the concept I'm afraid of. I don't know if this is something you use at school, but it's totally fine, I guess. Now at the position 3a, okay, the total energy is 1/2 mv squared minus mg times 3a, because it's below the point of 0 gravitational potential energy, and the elastic energy is 0 because the extension is 0. I mean, at its natural length, it has no extension, right? So these two expressions have to be equal because the total energy is conserved. Okay, so 1/2 mv squared minus mg3a is equal to 18 mg over 5. Actually, let me over 30. Let's make it 30. Okay, over 30a times 4a squared minus mg5a. So m cancels. Okay, so v squared over 2 becomes equal to 12/5 ga minus 2 ga. Okay, so v squared is 4 ga over 5. So the velocity is the square root of 4 ga over 5. Okay, this was part A. Did we write it somewhere? Yes, let's write it there. Okay, again, use the principle of conservation of mechanical energy to find, in terms of A, the distance of the particle below A when it first comes to instantaneous rest. Okay, let's draw another picture. I think it helps to draw pictures when you work with problems in mechanics, to be honest. At least it helps me. So, okay, we have the same spring, okay. So here I'm making an assumption. I'm assuming that the extension is 3a plus x at the point where it instantaneously stops, okay? And we will have to find x, okay? So this is so let's write it here maybe. So this is the position of instantaneous rest, and it's at the distance of 3a plus x. The GP is 0 up there like before, and we release it from the position of 5a. Okay, so let's call this position 1 and position 2. Okay, so again, the energy at 1 is equal to the energy at position 2, the total energy, right? What's the total energy at position 1? It's 18 mg over 5 times 2a squared over 6a, because it's extended by 2a compared to the natural length, minus mga times 5a. So the same as before, right? This is what we used. Where is it? Yes, it's the same as before. Okay, but now this must be equal to the gravitational potential energy at the position 3a plus x, which is equal to minus mg times 3a plus x. Actually, this is going to be confusing. So what I'm going to do is I'm going to go back here and grab this and do cut, and then do how do you do paste?
Underscore.
Oops, I didn't know I can talk. Okay, we cut it, but how do we add it back? Paste. Okay, sorry. Okay, so this is the energy at 1. We had our little adventure. I'm sorry. Okay, now the energy at point 2 is going to be minus mg times 3a plus x, right? Plus the elastic energy, which is going to be 18 mg over 5 times the extension. The extension is now just x, so x squared over 6a. Okay, I hope this makes sense. And the kinetic energy is 0 because it comes at an instantaneous rest. So the mg's cancel like before, I think, and we are left with the following. So minus 5a plus 12a over 5 is equal to minus 3a minus x plus 3x squared over 5a. Okay, so 3x squared over 5a minus x minus 2a squared is 0, and we can create a common denominator. Did I miss something? No, it looks good. So 3x squared over 5a minus 5ax over 5a minus wait, something is wrong. This is minus 2a squared over 5. I'm sorry, it skipped my attention. Okay, so this is let me see, this is 2a. Okay, sorry for that step, I messed it up. So 3x squared, okay, and then minus 2a squared over 5a is 0, and then since 5a is not 0, you can cancel the denominator, and we are left with this equation, 3x squared. Actually, let me use a clean page. So we don't have a clean page, so let's create a clean page. Okay, so 3x squared minus 5ax minus 2a squared is 0. So this is a quadratic equation. X1, 2 becomes 5a plus or minus 25a squared plus 24a squared. You can check for yourselves, over 6. Okay, and this yields two solutions. X1 is 2a and x2 is minus a third. Okay, now remember, what is x? We defined it as the extension below the natural length. Okay, so if x is 2a, this is the moment where we release the ball. So without the solution, we don't need it. Okay, and x2 is minus a thirds, which means that the extension is actually backwards and up here. So that's the first time it comes to a rest. So that's the position. What's that position? 3a plus x. So 3a minus a third, right, of a. So the position from a is thus 3a minus a third, or 8a over 3. And that's the answer. It makes sense to me. Please check my reasoning, and if something doesn't make sense, let me know in the comments. I always reply to comments. So let's move on to question 8, which is the last question in this paper. So we have that crazy situation over there. So a particle P of mass m is attached to one end of a fixed is attached to one end of a light inextensible string of length 4a. The other end of the string is attached to a fixed point O. The particle is held at the point A, where OA is 4a, and OA is horizontal as shown in figure 5. The particle is projected vertically downwards with speed 2 square root of ag. When the string makes an angle theta larger than 0 and smaller than pi over 2 with the downward vertical through O, and the string is still taut, the tension in the string is tau, T. Okay, air resistance is assumed to be negligible. Show that T is mg times 1 plus 3 cosine theta. Okay. It always helps to draw a scheme, as I keep saying in this paper. So this is the situation. This is the string. This is the vertical, and that's theta. Okay, and that's the mass. Okay, now how many forces do we have? We have the tension, right, from the string, and the mass mg. Okay, this undergoes circular motion, therefore it doesn't make sense to analyze mg. You might be tempted to analyze mg like this, for example. No, actually, what am I saying? Yeah, forgive me. I don't know what I was saying. Let's go one more time. So this is making a circular motion. Therefore, it makes sense to draw an axis that extends from the string and a perpendicular axis. Okay. So if I extend this a little bit, we see that if the angle is theta, this is also theta, and therefore this is also theta. Therefore, this component of the weight is mg sine theta, and this component of the weight that we need, okay, this component is mg cosine theta. And again, in other videos, I always say that whenever a component touches an angle, that's a cosine theta. Whenever a component does not touch the angle theta, like in this guy's case, then that's sine theta. Okay. All right. Are we done? No. Because the problem is that we don't know what the velocity is. Okay. So we have to find the velocity. So this is a really messy drawing I made, but I hope it makes sense. So we will take GP to be 0 at position. Let's call this position 1, and let's call this position 2. Okay. We need to find the height, which is the perpendicular distance, so that we can calculate the gravitational potential energy. So Let's find cosine theta first. So sorry, let's find h. So this is h. So cosine theta is h over 4a because that's 4a. So h is 4a cosine theta. Okay, and then we can use the principle of conservation of energy. So E1 is equal to E2. So at E1 we have 1/2 mv squared plus 0 potential energy equals 1/2 mv prime squared minus, I'm sorry, like before, minus mg times h, which is 4a cosine of theta. Okay, so if we carry out some calculations here, we can figure out, let me see. So we have 1/2 m, and then v squared is given as 2 square root of ag, so m times 4ag. So I'm plugging v squared for 2 square root of ag, okay? And it becomes 4ag, like that. Okay, plus I'm bringing this factor to the left-hand side, so plus 4mg a cosine theta. This is equal to 1/2 mv prime squared, okay? And let's solve for mv prime squared. You will see the reason in a minute. So mv prime squared is 4mga times 1 plus 2 cosine theta. Okay, now at position 2, we have that t minus mg cosine theta. We need the sum of all forces to point inwards, right? Because we have a circular motion. So t is positive, mg cosine theta is negative. So t minus mg cosine theta is mv prime squared over r. And this is why we solved for mv prime squared. So it's easier to work with. So t is mg cosine theta plus 1 over 4a, which is r, times 4 mga. So a cancels, 4 cancels as well. And then we have 1 plus 2 cosine theta. So t is mg times 1 plus 3 cosine theta. Okay, and we proved the first question, which was kind of hard. Okay, now B, find in terms of A and G the speed of P at the lowest point of its path. So they are asking for the speed of the particle when it reaches the bottom, pretty much. Okay, so to do that, we can use conservation of energy again. So part B, so we have 1/2 mv squared plus 0. Okay, so I'm taking 1/2 mv squared with this velocity. Okay, and then we take the gp to be 0 up there. Okay, gp is 0, becomes equal to 1/2 mv, let's take it to be double prime squared, okay, minus the potential energy, which is minus mg for a. Okay, so m cancels, and then we have 4ag plus 2ag is v double prime over 2 squared. So v double prime is equal to 12ag, which makes sense. It's a higher velocity because it's at the bottom, right? Now, we're done with B. Now, for part C and D, we have to read the next statement. There is a fixed horizontal peg here, okay? So let me raise this because we will need to do a new reasoning. So there is a fixed small horizontal peg at point B, which is at the distance 2a vertically below O. The peg is smooth and is perpendicular to the vertical plane of the motion of P and the string. The string comes into contact with the peg and P continues to move clockwise in the same vertical plane. The point C is such that CB is 2a and CB is horizontal as shown in figure 5. When the particle passes through C, the string is still taut. And then question C, find in terms of A and G the exact speed of the particle at the instant when it passes through C. Okay, so this is a little bit easier than it sounds because, let me see what I did. We can take the speed we just calculated here, okay, and we can take GP to be 0 down here now, okay, so we change where the GP equal to 0 is. By the way, you can take any point you want. It's gonna result in the same result, okay? So if GP is 0 down there, then when the particle is up there, its potential energy is 2 AmG, right? So the kinetic energy down there, so let's go write some stuff down. So C 1/2 mv double prime squared, which is the velocity we calculated, is going to be, let's plus 0. It's going to be 1/2 mv, let's do 3 dots, okay, 3 primes, something like that, okay, squared plus mg2a. Okay, I hope this makes sense. So m's cancel like before. So we have 1/2 m. Wait, why is m still there? Sorry, let's erase it. Times 12 ag is 1/2 v 3 primes squared plus 2ag. Okay, so v triple prime is the square root of 8ga. Okay, do we have more space? We do. Okay, this was part C. Now, part D, find in terms of M and G the tension in the string at the instant when P reaches O. Okay, so let's erase this yet again. Okay, so they ask us for the tension when the particle comes back there. Now the speed when it comes back there is the same as before, right? It's the same as the speed it started with, okay? Now the string is going to, so the particle is going to be up there, therefore tension is going to be downwards and the mass is going to be downwards, right? So let's calculate things. So T plus m times g is going to be equal to the velocity it had when it started because of conservation of energy. So it's going to be mv squared over r. So T is going to be minus mg plus m over 2a. Okay, this changes now. R is 2a because this radius becomes smaller, half of what it was before. Okay, so plus m over 2a times v squared, and we take v to be 2 times the square root of ag. That's the velocity we started with. So 4ag, so a cancels. And we end up finding that T is minus mg plus, this is 2 plus 2mg. So the tension is simply m times g. Okay, this was, okay, and yeah, we reached the end. There is nothing else, right? Okay. So this was a really challenging problem set for me, a past paper for me, okay, because it was the first time, I guess. But hey, now we have one more paper in our library, and hopefully I will find the time to keep solving papers like this. Okay, the focus will remain the physics papers. So units 1 to 6 for the AS and A level for Edexcel. And I plan to also keep solving past papers from England. Those are AS paper 1 and 2, and then A level papers 1, 2, and 3. That's advanced physics, okay? So I will keep solving papers as I find them, but this was a really nice challenge for me and a really nice change. So thank you to the subscriber who suggested it. So yeah, this is it, I guess. I'm gonna see you in the next video. Oh, again, 85% of the people who watch these videos do not subscribe. It's gonna do me a huge favor to subscribe, because hopefully eventually I will be able to, I don't know, make more content and more physics and more fun stuff, etc. So thank you guys for those of you who are following and subscribing. So I'm gonna see you in the next video. Bye.